Okay, so we'll just start today. So today we're going to do more induction. And the Dedekind piano axioms. Okay, so this is what we're going to start with. So I wanted to start with another proof by induction. So this is like the example from the handout. So I'm going to start with that so we kind of are just refreshed on what's going on. So example, we're going to start with a proof by induction is what we talked about. So prove, so we will prove that the sum from j is equal to 1 up to n of j is equal to n times n plus 1 divided by 2. Okay, so this is what we're going to prove. So we'll prove this. We'll do it by induction. Okay, so here, so we'll do the proof. Okay, so the proof will be by mathematical induction. With Pn here being the following formula. J is equal to 1 up to n of j is equal to n times n plus 1 divided by 2. Okay, so notice again that this proposition here is not a function, right? It just returns true or false, right? It's not like I'm going to get some other natural number outside of it. Okay? So there's two parts of a proof by induction. The two parts are the base case, okay, and the inductive step. So we'll start with the base case. Okay? So in the case n is equal to 1, so our inductive step, our base case could start at any number. It could start at 2, it could start at minus 1, but it only proves things after this number. Okay? Or it could be at 0. So sometimes it's useful to start at 0. Anyway, this one we're going to start at 1. In the case n is equal to 1, the left-hand side is the following. It's the sum from j is equal to 1 up to 1 of j, which is just 1. The right-hand side is the following. So this is the left-hand side. This is the right-hand side. So the right-hand side is, well, n times n plus 1 over 2. And this is equal to 1 times 1 plus 1 over 2, which is equal to 1. Okay? And since these sides are equal, we have shown P of 1 holds. I don't need to say P of 1 holds. It's technically redundant because it's like P of 1 is true, right? Or you can say we have shown P of 1, or you can say P of 1 holds. Either one's OK. Okay? Also notice that I didn't just like plug in 1 into both sides and like show that 1 is equal to 1. That's kind of a bad way. It doesn't read very well because you end up getting at a tautology and it looks weird. So if you say something like something about looking at the left-hand side or looking at the right-hand side, or you can even write a sentence is that it's easy to check that the left-hand side and the right-hand side are the same, right? Where you don't actually have to prove anything. Does that make sense? Okay. Yeah.
This is for induction.
Yeah.
This next chapter or is it?
This is chapter 3.
Okay.
Yeah. This is chapter 3. Yep. Excuse me. Okay, so now we start the inductive step. Okay, so we've done the base case. This is all the base case here. So the inductive step. Okay, we suppose and so we'll do k minus 1 today. Excuse me. We suppose p of k minus 1 and show p of k. Okay? It doesn't matter what we use here. We could have used n to n plus 1, k to k plus 1. We could have used, like we did, k minus 1 to k. If you're crazy, you can do n plus 1 to n plus 2 if you wanted to. It doesn't really matter what we do. It just needs to increment by 1. Okay? All right. All right, so we suppose pk minus 1, and we show pk. Okay, so suppose pk minus 1. Okay? That's what we're going to do, this thing. Okay, so now, at this stage, I've already done all my scratch work, and I kind of know how the proof is going to go. Okay, and what I'm going to do here is I'm going to break up the sum from j is equal to 1 up to k into j is equal to 1 up to k minus 1, and then add that extra term at the end. Okay, so this part of like seeing how it goes might involve a little bit of thinking when you're doing this in practice. Okay, so you might not have, you might have to fiddle a little bit. But then now that I know how it goes, I'm going to go back and write how it goes. Okay, does that make sense? Okay, so I'm just going to write this term here. And like I said, I was going to break it, but the strategy was to break it up into 2 pieces. The reason why I'm doing this is so that I can apply this formula that we know. So we're allowed to assume the formula for pk minus 1. Right? So that means when I plug in k minus 1 here and everywhere here, we know that this equation is true. That's part of the inductive hypothesis. Okay? So this equation here, we have this thing, and this is the first part. So this is k minus 1 times k minus 1 plus 1 over 2 plus k. And so this part here, this line, from this line to this line, is by inductive. And so this is inductive hypothesis. Because I have to have, in order for this to be an equality, right, I need to maintain the full sum, right? So this is the sum from j is equal to 1 to k minus 1. And then this thing goes to k, so you have to add it here. Okay? Just to remind you that this summation notation is like an integral. This is the starting point, and this is the ending point of the sum. Okay? And so I could start earlier, but I have to add this extra term where j is equal to k. Okay? So what's the inductive hypothesis? So when we say by inductive hypothesis, what exactly is the inductive hypothesis? So the inductive hypothesis is the thing that we suppose, pk minus 1. That's what allowed me to replace this thing here with this. Because again, I am assuming this equation holds, right, in the case that n is equal to k minus 1. Okay? All right, so that's what we did. We're applying the inductive hypothesis. All right. So now I'm just going to simplify this a bit. Okay, so this is k minus 1. And here we have k minus 1 plus 1. This is just k. And here's over 2. And then I'm going to do 2k over 2. Okay, so I'm just going to simplify this a little bit. So this is k squared minus k plus 2k over 2. And this is equal to, okay, well, this is going to be k squared plus k over 2, which is just k times k plus 1 divided by 2. Okay, and this shows pk, okay, which proves pk. pk was that this thing here was equal to this thing here. And again, what was the thing? This is the part that requires a little bit of thought, is that for this sum here, we can break it up into the previous case to get there. Okay, so there's for summation formulas, this is pretty typical that the thing looks like this. It's like you could replace this j here with anything you want, and then you could always break it up into the previous number of terms here, and then check that the result still works. Okay. For other types of proof, you're going to have to do some other things, but it always involves implying the inductive hypothesis. Okay. So now, what do I say? Since we've proved, right? Since we've proved the base case. So since, let me just erase all this too. So since the base case and the inductive step we are done. Okay, and that completes the proof. Questions on this? Yeah.
Could you theoretically use any variable aside from
K?
j?
J, yeah, exactly. Just like an integration here. I could have used an L here, or I could have used, you mean for
I
this?
was saying more specifically for like the p of something.
Oh yeah,
So
you can use whatever you want there. You
As
can
long
use
as it's
X,
just
you
not
can use
J.
Y. As long as you're not going to use the same variable elsewhere, you can use whatever. You can even go from n plus 1 to n plus 2 if you wanted to, right? Or you can go from n to n plus 1. You just have to make sure you increment once, and it doesn't matter what letter you choose your favorite letter. You can use a Greek crazy letter if you want. Yeah.
I might just be confused here, but how did you get from k squared minus k plus 2k over 2 to k squared plus k over 2?
Here,
Yeah, there.
I factored out a k,
Oh, okay.
right? So here, I just pulled out a k. You can read it this way too. So here, this is k squared plus k, if you multiply this out.
No, I mean, minus k plus.
You have a minus k, so
Oh,
from this step
okay.
to this
Yeah.
step?
Okay, I get it.
Yeah, here I distributed the k as well.
Okay,
Yeah,
that makes sense.
yeah.
Never mind.
Yeah, no problem. All right, cool. Yeah. Where what? What is k an element of? At the end, why is this here? Okay, so let me explain that step. So here's like a little, let me just, so this sum here to k, so this is really saying of j, or we could use another letter, like, or let's just keep up with what we were doing. This is 1 plus 2 plus dot 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 up to k minus 1 up to k. Okay? So what I did here is I broke this up into two parts, 1 plus 2 plus up to k minus 1, like this, plus k, like this. And this sum here is just really the sum from j is equal to 1 up to k minus 1 of j plus k. That's what I did. So that's what this sum means. It means you sum this function here from j is equal to 1 up to k minus 1. Why not write k is equal to 1? If you wrote k is equal to 1 here, then you'd be, and you kept this to be the same, then you'd have to write that this would be, I guess, k minus 1 times j. But that's not what we want to describe. We would like to describe a summation. Okay, yeah, okay. This particular summation. All right, does that answer his questions? Okay, cool. All right, so let me show you now why induction works, okay? So there's a bunch of different schemes for for axiomatizing the natural numbers, okay? And I'm going to give you one of them. And these are called the Dedekind-Peano axioms. So historically, what happened was that Well, people were proving things, okay, in the early 1700s. Okay, so Euler introduced the function notation, the function notation that we have now. And then they figured out what the definition of continuity was in the early 1800s. This is like by Cauchy and other people. And then later, they decided what a set was. And then even later, well, this is around the same time, is they decided what the natural numbers should be and what axioms they should satisfy in order to prove things completely rigorously. OK, so I'm just going to write down the axioms that they have. So these guys are Dedekind Peano axioms. OK, and these come from 1888 and 1889. OK, so they're kind of old. Yeah.
Did those two people work together, or were they developed separately?
These are two distinct publications around the same year, and I think they were aware of each other, what each other was doing, right? So Peano had a version before this, right? And then he refined them into, I think, either one of these versions. The reason why I guess people include his name is because he proved something interesting, which I'll say in a remark later, okay, about these axioms. Okay, so the natural numbers are defined to be a set n satisfying the following. Okay? So the first axiom is that 1 is an element of the natural numbers. It's not so important here that it's 1, but we just have some starting point. So I could have written this in a more abstract way where it said it had a starting point, but I don't really want to do that because it looks ugly. Okay? The second axiom says that so if for all n in the natural numbers, n plus 1 is also in the natural numbers. So sometimes this is called the successor axiom. Okay? All right, the third one. So the third one says, so for all n and m in the natural numbers, if n plus 1 is equal to m plus 1, this implies n is equal to m. Okay? Okay, P4 is the following. So it says that for all n in the natural numbers, n plus 1 is not equal to 1. Okay, so here this is the special distinguished element. Like I said before, we could have replaced this with 0 or some other starting point, right? Yeah?
Third axiom, not if and only if? Like, isn't that true in the reverse?
So it is true in the reverse. So I guess we could put it as an if and only if as well. You know, I think it's logically equivalent. Yeah. Yeah. So okay, so let's do this one, last one. And so this is really the main point here. So if S is a set of natural numbers, then, and 1 is an element of S, and for all n in the natural numbers, as n is an element of S implies n plus 1 is an element of S. So if every single element has a successor, let's write it like this. Then this implies that S is equal to all of the natural numbers. Okay, so this is a really important one here. Okay, so this, these two things here imply that S is all of the natural numbers. So if you have the starting point and you have the next one for every guy in your set, then that's going to be all of the natural numbers. Okay. Does that make sense, these things?
N plus 1 is in the set of S?
Yep. So if n is in the S, this implies n plus 1. That's a plus. Yeah. Does it look like a divide? Yeah.
No, it looks like an H.
Okay. No. N plus 1. Yeah, thanks. Okay. So that's what we have there. Okay, so let me make some remarks here. So kind of remarks. Okay, so the first remark that I want to make is the symbol m plus 1 is often replaced by S of m. So for the successor of m, okay? But I just wrote it as m plus 1 so it looks more familiar. People care about this sometimes because this thing technically it looks like it takes 2 inputs here, and this is a unary thing, a unary function, meaning it takes 1 input, okay? Some people care about that. But if you're reading it in other places, it may look like this, but when you see this, it really just means m plus 1, okay? Other things. Okay, so Dedekind proved, this is kind of a big one, proved, and this is what I mentioned before, that the natural numbers are unique in a certain sense. So the technical word is categorical, right? But he proved that if you have a collection of things that behave in this way, that they're all essentially the same. Note that this doesn't, that this, in a certain sense, accounts for the starting point here. Okay, so here, you know, I could have started at 0 and I could have started at 1. Right, which brings me to the third point is that, well, that's exactly what I wanted to say, is that you know, we could have started replaced 1 with 0. Okay, and we would have essentially gotten the same thing. By essentially, I mean, you know, this ordering thing where you have successors and they behave the way that they do. 1
How do you replace and how's
is just a symbol. So the whole point is that it's just a symbol. So 0 and 1 are just symbols, right? And that we define the natural numbers in such a way that you have successors, so that you have the next guy. Yeah.
Well, I think what he's saying is that if you replace an axiom 1 0 with 1,
Yeah.
then 4 doesn't make sense because you essentially have.
So yeah, and here you'd replace this with 0 as well, right? So you'd say n plus, or sorry,
Do you replace? I would think you would replace n. With
so
0.
n plus 1 is not equal to 0, is what you'd have here.
Oh,
Right?
okay.
So in this one, you'd have n plus 1 is not equal to 0 because you can't have an, so 0 is not the next number of anything. Right? Does that make sense? If you decided to start at 0. Yeah.
So in the 0 and 1 are just stand-ins for starting point.
Yeah. 0 and 1s are stand-ins for starting point in this
Okay.
thing. Yeah.
There's no other starting points.
-2. You can start at -2 in this thing.
Oh, you really start.
Yeah. You can start at, you can start, it's a starting point. Right?
Oh, so you
Okay.
choose one.
Yeah. So there's another set of axioms called piano arithmetic, which are not the Dedekind piano axioms. Which this brings me to my next point, right? So, and the next point is that, so 4, right? So these axioms are not the famous piano arithmetic axioms. Used in Gödel's incompleteness theorem. So in this setup, let me just make it's kind of fun to talk about it. So in this setup here, you want to make sense of what multiplication means and what addition means. So here I said that we had just this successor function, really. It's really, this whole thing depends on this. So there's a kind of a more, you can add more axioms to this, right? And then and modify this last axiom here, okay, to actually an infinite number of axioms, right? And then you can talk about multiplication, right? And you can talk about ring structure or semi-ring structure. And in the semi-ring structure, in order to talk about identities, this more than just the starting point matters. Okay? So in that setup, right, the 1 and 0 need to be pinned down. Okay? So in that setup, it's very important. But in this setup, when you're just talking about the sequence of numbers, right, it's not so important that where you start, right? But if you were, which we will talk about in a bit maybe, is that this Peano arithmetic, which is distinct from the Dedekind-Peano axioms in that it has more stuff, right? You do care about the starting point. Yeah? Well, that one, yeah. So this one, this Peano arithmetic, encodes like the information about multiplication and addition, which is not encoded in these axioms. And in that one, the additive identity and multiplicative identity matter, right? And those are 0 and 1. Okay, does that make sense? Okay, so so now I want to show you guys, okay, how these axioms here, right, will give you the proof by induction. Okay, so why do these things lead to induction? And let me just give you kind of a spoiler, is that you guys could probably do this already, right? If I were to ask you to, I have faith that you guys could do this. But really baked into this axiom here is the induction axiom. So it's almost like we define the natural numbers so that proof by inductions work. Does that make sense? Proof by induction works because we define it to be that way. But let me just go through the steps so you guys can see. And I guess since I'm already talking about it, I can also remark that sometimes instead of phrasing it like this, you'll see textbooks, they'll phrase Peano arithmetic in such a way so that, no, sorry, not Peano arithmetic, these Dedekind-Peano axioms in such a way such that this thing, instead of looking like this, it just says, if you have the base case and you have the next case, then the proposition is true, right? So it'll say proof by induction works in symbols. Okay, so let me do this theorem now. So here's the theorem that I wanted to prove. So theorem. So this is why induction works. Sounds like Smash Brothers or something. Okay? Yeah. Okay, so P of n be a predicate about the natural numbers. So it has a free variable about the numbers, free variable where n varies over the natural numbers. Okay, so if one, so if p of 1 and 2 for all n in the natural numbers, p of n implies p of n plus 1, right, then, so this is an and statement. Then for all n in the natural numbers, p of n. Okay. So let me show you. Here's the proof. Okay. So okay, so we're going to let S be the set of n in the natural numbers such that p of n. Okay? So this is the set of numbers where p of n holds. Okay, does that make sense? So you determine membership of this set by, by testing this thing. Okay, so here, by property 1 in the statement, we have that 1 is an element of S. Okay, since P of 1 is true, P of 1, right, 1 is an element of S. Okay, by property 2, so if n is an element of S, then n plus 1 is an element of S. Okay, so what have we gotten? This is for all n in the natural numbers. So now we get to apply this axiom here. So this is the axiom of induction. Sometimes this is called the axiom of induction. And so here we have a set where 1 is in here and n plus 1 is in here, right? So by applying P5, this is called the axiom of induction. Sometimes we get that S is equal to the natural numbers. So P5 said, so I just erase it, but P5 said, I'll copy it over here. So P5, what did it say? It said that if 1 is an element of S, and for all n in the natural numbers, here, if n is an element of S and implies n plus 1 is an element of S, so this whole thing implies that S is equal to the natural numbers. Okay, so this is the axiom of induction. And we have 1 is an element of S, and we have the property that this is in here implies this is in here. That's because this implies this. Okay? So P of n implies P of n plus 1, and we define this set to be the set of elements such that P of n holds. That make sense? Okay. So we get S is equal to the natural numbers, and hence, okay, so n is equal to the set of n and n such that P of n. Hence, P of n is true. Hence, is true for all n. Does that make sense? Let me just write the big point here. So cooked up to make induction work. It's part of the definition of the natural number. Induction's part of the definition of the natural numbers. It's kind of an intuitive thing. I drew that cartoon for you guys the other day, but the whole point is that we make the axioms so that induction works. Not more than this. We'll have to use it. We use it all the time. We've already been using it in the previous class, but I just didn't tell you guys that we were using it. Now you guys know. And now you guys are aware.
It's like behind the scenes.
This is behind the scenes. This is under the hood of what this induction's going on. Okay, so this is what it's doing. Like, why are we doing that, right? Well, it actually turns out that it's defined to be this way. That's how we define the natural numbers. We define the natural numbers to have an induction property, so that we can do these proof by inductions. proofs by induction. Okay, any questions on that? Okay, so let's do another proof. Okay, so we'll do one more proof, and then so let's do another example. I mean, I can't let math majors go, right, without knowing why we're doing proof by induction. Okay, so let's prove that every natural number is even or odd. Okay, so let's prove that. Okay, so what was the definition of even, and what was the definition of odd? Yeah.
Even is 2k and odd is 2k plus 1.
Exactly. Even is 2k and odd is 2k plus 1. This was something that we assumed previously. We now can prove it. Okay, so let's do a proof of this. So the proof. So we will prove this by induction. Okay, so here P of n is a statement that there exists a k, let's say in the integers, such that n is equal to 2k, or there exists a k in the integers such that, let's do an or here, or there exists a k in the integers such that n is equal to 2k plus 1. Okay? This is a bound variable, so again, we can replace this k with whatever we want here. It's like, you know, a variable of integration. Same thing, you know?
Couldn't your z be an n? K is an element of integers instead of k is an
I'm going to do a z because it could be 0, right? So it could be 0. So I'm going to do z here. Yeah. Yeah. We could do n if we included 0. Maybe we should have started at 0 the whole class, but yeah.
Why is it there exists? Why is it not like for all z, or for all k and z, or for all k and z, k is either, n is either 2k or 2k plus 1?
So that would be saying, so like fix n. Give me an n. Your favorite n.
4.
Okay. So it's saying, so for the particular n is equal to 4, it would be saying for all k, 4 is equal to 2k, or 4 is equal to 2k plus 1, right? So that would be saying that like 4 is equal to, you know, not only just 2 times 4, but it would be 3 times 4, or 3 times 2, you know, 4 times 2, 5 times 2. It would say that it's true for all of them. And since those even numbers are distinct, it's not true. Does that make sense?
Yeah.
It's like this. If you did it for all, it would be like saying that n, your number was 4, would be equal to 2. It'd be equal to 4. It'd be equal to 6. And then on this side, it'd be or it's equal to this, this, this. And it'd asking that it'd be equal to multiple numbers, which can't be the case. Okay. Yeah. Okay, so let's do the proof. Oh, we started this. So proof this. So the base case. And we can start at n is equal to 1, or we can start at n is equal to 0. It doesn't matter the starting point. So n is equal to 1. So 1 is equal to 2 times 0 plus 1. So it is odd. And P of 1 is true. Okay, so let's do the inductive step. Okay, so the inductive step is we suppose P of n, or P of k. Let's do suppose P of n and prove n plus 1. Okay, and here we have to break it up into two cases. P of n says n is either even or odd. Okay, so P of n, so suppose n is even. So n is equal to 2k for some k. Okay, and so this implies that n plus 1 is equal to 2k plus 1, which is odd. Odd. So P of n plus 1 holds in this case. All right? So let's suppose n is even. So suppose n is odd. Hopefully I didn't say. So here we suppose n is odd. Okay? So n is equal to 2k plus 1 for some k in z. Okay? So this implies that n plus 1 is equal to 2k plus 1, which is 2k plus 2, which is 2 times k plus 1. Okay? So this proves P of n plus 1. So this proves P of n plus 1 because it's even. Since n plus 1 is even. Okay, oh, I can't quite conclude that. So now we've proved the inductive step, and we proved the inductive step. Within the inductive step, we did a proof by cases. Okay, we had the case when n was even. We had the case when n was odd. We added one, and we saw that it was either even or odd. And actually, we proved that if if a number is even, its successor is odd, and if a number is odd, its successor is even. Okay. Okay. Since we proved the inductive step, the base case, and the inductive step, we completed our proof by induction. Okay, and that's the end of the proof. Okay. Any questions on this proof? Okay. So with the last couple minutes of time, why don't you guys take out the first word? Actually, I forgot to tell you about the homework problem. So, so there's going to be a homework problem very similar to this one that I want to show you guys. So let me just, before we're doing that, so homework problem. So this is not on, the next homework's homework 5, right? So homework 6 will be this. Okay? So fix m a natural number. Okay? Show for every n in the natural numbers, there exists some a, an element of the non-negative integers, and r, let's say r with r being bigger than or equal to 0 but less than m, such that n is equal to ma plus r. Okay? So here, note that if m is equal to 2, right, then this is just saying just saying every natural number is even or odd. Okay, so it's saying that you can, essentially this is a division with remainder. Okay, so you can divide n into pieces, chops of n, right, m, and then you have some remainder where the remainder is in between 0 and m. Does that make sense? So this is something that you can prove now. Right? It lets you chop up numbers into things like this. Okay, so with the remainder of the time, why don't you guys try and work on and ask me questions about handout 1? So, or sorry, the handout 3. So you should be able to do all of handout 3 now. So this is induction. Okay.